Good morning, everybody. Welcome to the talk. So I built it around what my impression was around AI when I started working with it, or I guess LLMs in general. So I kind of biased it towards kernel engineers, which I'd like to think I'm one. So we'll see how it goes. I start with this brief explanation of what really is LLMs or AI and how do they work. Bear with me if you already know all of that. So really, LLMs are kind of stupid, right? Think of them as this fancy pattern matching engines, and they're pretty good at guessing what the next word of a sentence is based on their experience or their learning from stuff that's on the internet. Unlike traditional programs, they are probabilistic. So basically, there are odds for them to answer or to guess the next word in a certain way. And they do it based on the patterns they learned, again, from the internet. The large in LLMs refers to the parameter count. So when you say like the 7B or 1T, it actually refers to how many parameters are in that model. And really, the way I kind of internalize that is LLMs are this massive state machine. So in the kernel, we have a whole bunch of state machines. Think of it as this one big state machine where the transitions between states are more based on odds rather than being deterministic, which is a bit weird for like when you think about a computer program. It also uses the transformer architecture, which acts kind of like humans, where it allows the LLM to kind of narrow down on a certain piece of code, so you can give it a whole bunch of context. But when it does its work, it's actually going to be looking at a fairly narrow area to dig deeply into that. We have some examples of LLMs, both public and private, open source or not. And this is really an example of how it works, right? You give it a beginning of the sentence, and it looks back at the experience it picked up from searching stuff online, and it does it best to kind of guess what the next word in the sentence would be. You can actually see that all three answers apply, right? We have kernel code in C, we have kernel code in Rust and in Python. So in theory, all three are the right answer. But C is the more right answer, and so it's more likely to pick C instead of the other answers. There are some keywords that are being thrown around here. So as I said, the large refers to the number of parameters in the LLM. So when you say 70 billion models, literally means it has 70 billion parameters that it learned from within that model. We have this concept of context windows, which is, if you're thinking back to the kernel, it's like a working set, the amount of stuff you can put into your memory. The bigger the context is, the more stuff you can throw into that LLM, and the more complex work that it can do for you. And right now, context windows, that's one of the things that's the race to grow is ongoing. Different LLMs try to increase that context window because it allows way more possibilities. We also have this concept of temperature, which is how probabilistic the LLM is, or how likely it is to give the right answer or venture somewhere else. In the previous slide, we had the example of C or Rust. So the more you crank up the temperature parameter, the more likely it is to go and explore different areas that might or might not be correct. In general, if you're writing code, it's best not to do too much experimentations and actually get the right answer. This is my idea of, at some point, someone will ask me, hey, are LLMs going to replace us humans? Like, in 5 years, is it all going to be kernel engineering LLMs that will come instead of us? And I don't think that will be the case. I think LLMs are just another fancy compiler, right? Back in the 50s, 60s, everyone were working in assembler, right? And then C showed up. And we didn't stop coding in assembly because C was suddenly perfect. C isn't perfect, but we stopped doing it because C is good enough and we're more productive coding in C. And to me, LLMs are a very similar trade-off. They're not perfect yet, but at some point they will be good enough to make us more productive. And just like we didn't stop doing assembly altogether, the kernel still has a whole bunch of assembly code in it, we can always revert back to C and use C where we feel we need to, and where we feel that we as humans have an advantage. And then each abstraction layer had this resistance, right? We had the whole real programmers use assembly in the past, right? You can fine-tune the registers that your program will run on, and it sounded like you know what you're doing. And now this is real programmers use C for very similar reasons when the LLM topic comes up. So like to me, the insight I have in my head is LLMs don't replace programmers any more than C compilers replaced assembly programmers, right? It's not like assembly programmers suddenly lost their job and went to be unemployed. They adjusted and they became more effective doing what they're doing. And LLMs will do the same thing. They will make us more productive, and they will do it just at a very different abstraction level. So this is an example of a patch that landed upstream a couple of months ago. It replaced open-coded hash table implementation with the standard API we have in hashtable.h. The whole patch, starting from the code changes to the commit description, was written completely by AI. The only thing I did there was to review the code and actually test it to make sure it works. This is just a small snippet, and I'll talk a bit about what the colors mean there in the next slide. But you can find this patch online, and I have references at the end of the slides if you really want to look it up. So this is a great example of what LLMs are great at doing right now. You give it a small, well-defined task, and it goes and does it. And you notice that this patch isn't, hey, LLM, go write me a driver for my new hardware. Instead, it's a very specific, convert this specific hash to use our standard API. And in this case, LLM act like Coccinelle on steroids. If you know the tool Coccinelle that does all the transformations. Here it understands context. It understands that it might need to rename variables. It understands that it might need to update documentation. It's smart that way, right? This change was also very easy for human reviewers to look at. In practice, we changed 7 lines of code at the end. It was easy both for me and the maintainer of the subsystem to take a look at it, see that it's correct, and move on. For us who are not native English speakers, it also helps with writing a good commit message. It is a common issue in kernel world where sometimes writing the commit message can be more difficult than actually writing the code change. And it definitely helps there, both with language barriers, but also kind of to unblock that writer's block and help you get started somewhere where you can go ahead and fine-tune. It also means that larger tasks like, hey, LLM, can you replace all the open-coded implementations in the kernel with the hashtable.h one, they actually become tractable, not as one command, but as a project that someone can tackle and go over all the places that need to do the conversion. It opens the doors to cleaning up a whole bunch of technical debt we had in the kernel that no one really wanted to tackle right now. If you look back at the previous slide, you also notice that the LLM was smart enough to understand that variables need to be changed. So in the open-coded implementation, hash size is just 128 buckets for the hash table. But in our standard API, the size is spelled out in bits. And the LLM knew by itself that it needs to do that conversion to go from 100 to 128 to 2 to the power of 7, which is the same number, but it did it all by himself. It also understood that the part in green is really just a masking operation. It's not some weird math thing that's going on. LLM figured out that we're masking to get to the right bucket, and it knew that it doesn't need to copy that code somewhere else. It doesn't need to do anything with it. It just needs to call the standard API because the standard API already does it for us. The second one is you don't only have to write actual kernel code with it, you can also write a bunch of the tooling around the kernel with it. Working on the stable kernel, we see many cases where git log might have a kernel reference. If you think of like the fixes tags, fixes something and it points to a commit, we have quite a few kernel commits that don't exist. Either the commit pointed by the fixes tag isn't there at all, or it's pointing at the wrong commit, it's pointing at the wrong SHA-1, or sometimes the SHA-1 is actually short, so it's ambiguous. So it might actually resolve to 3, 4 separate commits. And it is an issue we kept hitting, and we kept kind of ignoring it and pushing it to the side, because it doesn't happen too often. But with AI, fixing this actually became fairly cheap. We can go ahead and ask AI, hey, can you please write us a tool that addresses this problem and describe it in detail and get back a tool that just works for us? So if you look at the scripts directory in your kernel repo, you will find the git resolve tool, which was also written by LLM fairly quickly as a response to the need to have a tool like that. If you look inside the script, you will also notice there is a fairly comprehensive test suite, which is fairly unique for stuff under the scripts directory. Usually people just write something quickly and throw it out there. There's no error checking. AI isn't lazy. If you ask AI to provide you a test suite to make sure you don't break it in the future, it will go ahead and do that. It won't give you a frowny face. It will get the job done, right? And all of this went from just an idea of, hey, we need a tool like that, to having something that is ready to be submitted to the mailing list upstream within minutes. I think I spent 10, 20 minutes, because I already had a set of examples where it's broken. I asked to write the tool. I made sure that the code made sense, and I tested it. At that point, it was fairly ready to go out. If you look at how long it would take a regular engineer to write that, you're looking at half a day at a minimum, right? Back and forth. And this was cheap to do, right? In the sense of time and investment of effort. So as I said, great test suite. There's also error checking, which is another thing that's fairly rare for stuff in the scripts directory. It doesn't assume that everything will go just great. It also makes sure that if things fail, they fail nicely. And this tool is now being used daily by quite a few folks. It's there in the scripts directory. As I said, it's already upstream. Give it a shot if that's the problem you're facing as well. Let's go back to a bit of theory before we move forward. There's this concept of embeddings that LLMs use. What are embeddings? They're kind of like the compiler intermediate language. You know, when you compile code, it turns it into intermediate language that is not really readable, but it's something that the backend compiler can actually take and work on. So embeddings are just like that. They turn human language into something that the model can process mathematically. Just like the compiler converts C to assembly, embeddings will convert text to vectors. But the important thing there is that they preserve the semantic meaning and not just the syntax. So it means that similar concepts, and not words, concepts, will cluster together in vector space. So if I say null pointer dereference, or I say NPE, even though it's completely separate words, the vectors will actually be very, very close to each other, which means that this opens the door to being able to search by meaning and not by words, and not just by like keywords inside the kernel tree. The magic is that the mathematical operations on embeddings, that they correspond to the semantic operations of like how similar the concept is to another concept, instead of how similar the keyword is to another keyword. For kernel work, it means it becomes easy for us to find things that are similar, either similar commits or similar coding structures, and not just similar terminology. This also opens the door to RAG, which is a way for us to solve another fundamental issue with LLMs, is that they tend to make up stuff when they don't know the answer. LLM will rarely tell you, hey, I don't know. It will go ahead and make something up. It will invent something that might be completely not true, which is really annoying when you try and get it to write code. It can come up with random kernel functions that don't exist, kernel structures that don't make any sense, which is a pain. So RAG is a way to kind of ground it into actual knowledge. RAG is like giving LLM access to the documentation while it's running and doing its job. It doesn't have to try and remember everything. So instead of trying to remember every single kernel API, it can just look up relevant information when it needs to, just like humans use documentation. And it helps prevent the hallucination problem by grounding it in real data that we pass to the LLM. So it stops making up stuff that's not true. The retrieval part, so RAG is two things. One is that we store information in, and then we get information out when we need it. The retrieval step is an important one, but since we use embeddings, we can easily dig up similar concepts out of our code base and out of the history. This also helps us solve, LLMs have this issue that they were trained on data, and data has a date cutoff, means it got trained on data up to, let's say, March of this year. So if the kernel has got new functionality since March, LLMs don't know anything about it, right? So if I ask it, for example, to do some work on folios, which are relatively new, it might not know of any new functions that are out there. And this is a way to solve that issue. We kind of can feed that knowledge to the LLM and actually have it work on information that is not within what the LLM was trained to do. How can we tie this to kernel development, you ask? So one, it helps us ground the LLM. So this is the simple one, basic, it stops making up stuff. But also, this is how we can teach AI about kernel-specific patterns. We show examples from our code base of how things are done. It also means that by grounding it into our kernel code base, we can make AI explain every decision, and we can trace it to historical examples. So instead of the AI just telling us, hey, I think this is true, it can also say, I think this is true because of this example and that example. It could show evidence of its work. It means that the AI is able to look at our stored embeddings and can say, hey, I want to semantically look for commits that are related to a concept, to give you relevant examples or to help me move forward with my research, and not just the keyword matches within our code base. We also can connect AI directly to our Git tree. AI knows how to run Git commands. AI knows how to operate on code. There's no reason we can't tell AI to go ahead and dig into the Git history. It's kind of like giving junior developer Git access type of thing. That's about the level now. And AI can go ahead and try and learn things about the Git repo all on its own. It doesn't need to ask me, or it doesn't need me to tell it what other commits touch the file. It can run git blame by itself. It can learn from what happened in the history. And it can use that knowledge to improve its research. It means we remove kind of that information bottleneck. Humans suck in interpreting data. And we just remove the human out of the loop. We let AI do everything on its own, starting from the investigation step, all the way to actually providing us with decisions based on what it learned. It kind of takes the whole inefficiency of humans out of this process. It also enables us to do iterative investigation. We can kind of let AI to go research. We can tell it instead, like if you go online to ChatGPT, you put in a question, you get an answer, and then you have to put the next question. In this scenario, you can just tell AI, hey, go investigate and come back to me when you actually dug into the problem and you solved the issue at the core of my problem, instead of coming back to me and me trying to keep it on track. That approach of me trying to update AI makes it lose context. Because I, as a human, am not good at being able to tell exactly or I'm not good at expressing what I really want to express to the AI. And with this, it takes the inefficiency out of the loop. And it can access all the Git history on its own. It can look through git log, git blame. It can run bisections on its own if it wants to. The AI is pretty smart as far as running tool goes. This is a real challenge we're facing. The scale of the kernel is quite large, and if you look at the raw numbers, to do backports efficiently, the stable maintainer would need to review 100 patches every day, including weekends, including holidays. There's no breaks, to find about 5 to 10 commits that need to be backported every day. It's a very tedious and frustrating process. It can drive you crazy. And it's not something that scales, right? You can't really keep doing this long term and maintain in a sustainable way. And also sometimes critical fixes slip through the cracks, right? Especially if they don't have obvious words in the commit message, if they don't say that they fix a bug, if it's just some technical description, and it doesn't have the stable tag, it might get missed and it might not land in the stable tree, and it could be a fix that affects real users, which is really important, right? The manual process also doesn't scale with the amount of stable branches we have, right? We don't maintain just one LTS, we have 6 LTSs. So for each of them, we need to do the evaluation of, hey, should this be backported to that stable branch? So the number of acts of research we need to do to determine where each backport should go is massive. It's not something that humans scale to do. And as I mentioned before, humans also suck and are inconsistent. So if I made one decision on Monday, I might make a different one on Friday just because things happen. I may be more tired, maybe I have more energy, maybe I understand things differently, who knows? Humans are very inconsistent. And so we need help with tackling the backport work. So we had Autosel for a while now, and before it was very primitive. It used the keyword system. The first edition of Autosel was just looking for words, fix, correct, crash, stuff like that. It would then score a commit based on how many keywords it found, and we would kind of try and do our best with that. So Autosel got rewritten to use AI and LLMs completely. And really, right now, it acts as another stable kernel maintainer. But this stable kernel maintainer is very special because it remembers every single backporting decision we did throughout the life of the stable kernel tree for decades, right? Autosel, the tool, builds a reg vector database. It learns from the existing backport decisions in all of our stable branches, and then it's able to classify new commits that we present to it based on that historical research. Not only that historical research, the tool can also go ahead and research using Git into the kernel tree to help better understand whether a certain commit should be backported to that specific code base. So it might do the research work on a 6.15 tree and have one decision, and then it might look on a 5.4 tree and reach a different conclusion just because the code base is different. It's not replacing us, right? It's not here to replace maintainers and do the work automatically, but it helps narrow down that 100 commit range that we were talking before to something smaller and something more tractable for the human maintainers to review. At the end, it will present it to us for review, and at the end, the humans are the ones who will decide whether a certain commit should be backported or not. LLMs are great at that because they also provide us an explanation of why it thought it needs to be backported. It will give us this brief blurb of text of saying, hey, I think the certain commits need to be backported because I saw 3 similar commits that were backported, or I researched the Git repo and I decided because of this function, it needs the fix, so it should be backported in there. And you can see on the Autosel mail send out, there's a block of text now under the scissor line with the full explanation. So reviewers also have access to that data. If you get an Autosel email from me, open the patch, open the mail, look in the middle, and you will have explanation of why the LLM thinks that this commit should be backported. This is really pattern matching at scale, right? We have hundreds, thousands of commits. We have tens of thousands of commits that need to be reviewed every release cycle. And this is really AI doing work at scale for us already. It can learn to work, or it can learn to use Git like an experienced maintainer, right? It can follow leads, it can check history, it can find patterns. It can trace complex relationships like within history. It can look at a fix it dug up using Git, and it can say, hey, this fix from 2 years ago is an issue, so we actually should be backporting commits like that to the stable trees. It can also pursue hunches, and it happens fairly often that you ask it to investigate one commit, and it will come back and it will respond to that commit, but it will also say, hey, there are 3 other similar commits that we haven't backported, maybe you want to look at them too, and provide similar explanation to those, which really help us close gaps as far as the backporting goes to like all the historical trees. It also runs in parallel. Humans can only kind of do one thing at a time. Like we can jump between things, but we can really focus just on one thing. AI can do a bunch of things in parallel. It can investigate multiple like thinking streams in parallel. It can investigate different functions, different files, different drivers. In parallel, so it's also relatively quick. It can do a lot more investigative work than a human could possibly do at a given amount of time. So really, it kind of switches, or it kind of moves AI from being a processor, where you can ask a question and you get a response, to having like this AI agent investigator that goes ahead and does work for us and help us do our work better. So it's proactive instead of kind of reacting to our questions that we throw its way. Now you might notice I haven't mentioned any like specific AI in person. Like I didn't say I'm using ChatGPT, I'm using Cloud or whatever, because we're not using any one specific LLM. We're kind of using all of them, right? Each LLM has its own strengths and weaknesses. Some LLMs are kind of better at coding, some are better at reasoning, et cetera, et cetera. So instead of relying on this one expert LLM, we have multiple expert reviewers that we refer to for each commit. Different models have different training data and biases. They do things differently. So instead of asking one, we cross-validate between models, both to catch hallucinations. So if only one model kind of says something, it's probably wrong, and it's probably, we should ignore that one. But also to help us reach a correct conclusion if there is a legitimate disagreement between multiple LLMs. If you look at the example below, this is kind of a real one I had for one of the commits when I was making the slides. You see 2 LLMs agree, and they provide their reasoning to why, and then one LLM was not sure. But instead of saying also like why they disagree or not, they're also able to provide you a score, a confidence level, at what level do they think they are really confident that something should be backported or not. And we can take the score and we can set our threshold as far as high or low as we want. And we can use that to filter out commits that actually we should be looking at reviewing for backporting, or just put them aside because they probably should not be backported. Yeah, it's fairly tunable, so it depends on how your risk for appetite or how many commits you want to review at a given day. You can kind of play with that a little bit. Switching topics completely, about 1.5 years ago, the kernel decided it wants to assign its own CVs. Sadly, we don't have infrastructure to assign CVs, to review CVs, to score them, to send them out to the, forgot the names, to kind of get them actually the ideas assigned. And so what we did for a month or two is sit down and write really hacky bash scripts that were really shameful. We skipped any error testing. It was bad, bad, bad. And about 1 year after we caught up with everything, we looked back and we said, OK, this is horrible. We need to deal with the technical debt before it comes back to bite us. And so we started rewriting all our CV tools in Rust, because Rust is what the cool kids do these days. So we tried to adapt. The problem is we don't know Rust that well, right? We're kind of kernel engineers, like Greg and me. We want to know C. Our Rust is not good. But LLMs know Rust fairly well, surprisingly. They actually know Rust really well if you also provide them a bunch of examples and code to start with. So the work to convert our hacky bash scripts into actual good Rust code that comes with tests was fairly easy. We could really just feed it through LLM and get something that looks reasonable to us and help us end up with code that is cleaner, nicer, prettier, something that other people can dive into and start working with us on it, right? If you look at this hacky bash script, it usually scares people. They look at it and they turn away and they wish us the best. But Rust code is fairly easy to understand. It's kind of easy for humans to interpret and to work on. LLMs infer things from usage. So bash scripts don't have types, for example, right? LLMs can figure it out. They see how the bash script uses the variable, and they know what type to assign to that variable. LLMs are also good at being efficient. So many algorithms we had in the past are really, really bad. We did things that are simple, just to keep our bash script simple and easy to write. But with the volume of CVs we assign, with the volume of kernel commits we need to go through, our scripts used to take hours to run in the past, just to be able to search up stuff, to assign CVs, to make sure the CVs wasn't already assigned for something. And we reduced it to a matter of minutes, if not within the seconds, right? Improving algorithms, doing like Rust lookup with the hash map thing Rust has, instead of us doing O and to the power of 2 lookups, just because they're easier to code in bash. This is an example of basically the translation that Rust is able to do for us. You don't have to know Rust to see that the part at the bottom is way easier to understand. The intent is better transferred through that code rather than what we had before, right? With the first bit, you have to go investigate what process.sh does. You have to go figure out, like, what are we reading, why are we reading. There's no error handling in the bash code, if you noticed, right? LLMs are really good at helping us get away from that technical debt. So when we finish that whole conversion and our tools are very rusty and very cool and easy to work and fast, we hit a similar problem to the backport problem. Like, well, we have so many commits that we have to evaluate and decide whether we assign them a CV or not, and there's way too many. Every bug fix could be a security fix, potentially, right? So we have to go through each of the backports. And the line between a bug and vulnerability is fairly blurry, right? You can argue usually each way. That's why when we assign CVs, it's a vote through 3 people, and then 2 of the 3 people have to agree. And it's not good to miss CV assignments, right? It affects users. It keeps them vulnerable. Downstream distros might not patch for that issue. So it's a risk that we really want to get away from. Also, assigning too many CVs is an issue. The false positives cause like unnecessary patches, too much turmoil, overhead, the whole crying wolf part, right? We don't want to lose trust in us by assigning CVs to everything, even if it's not a real vulnerability, we want to be really good at assigning CVs. Security expertise is also hard to come by. It's hard to kind of drag people to help us here. The folks who are security experts rarely want to spend hours of their day reviewing kernel commits and decide whether they should be assigned a CV or not. They can probably be better paid elsewhere, right? We also want to be consistent between us. As I said, humans are really inconsistent machines, and this is something that is very important. Security is a big, important thing, right? We don't want to give different decisions. We want to give the right decision at the end of the day. Humans are inconsistent, but LLMs tend to be way more consistent than us. This is really a very basic definition of what is a kernel CV challenge, right? You find the slide is actually kind of similar to the one we had for the stable backports one, right? I still think I spoke about this one. Yeah, sorry, extra slide, ignore. And so we realized, hey, we're actually solving a very similar problem to the backports challenge, right? It's just a different question and a different answer that we expect to get. One of them is, hey, should they be backporting this commit to all their stable trees? And the other one, hey, should this stable commit be assigned a CV ID? And in practice, Autosel and the new CV classifier tool are siblings. They kind of have the same core library that was abstracted into a library called commit classifier. And they just ask different questions, and they get different answers. The commit classifier is the shared brain between both of them. The voting part, the reg concepts of looking into the existing code and building a vector database, and the Git accesses, the Git research. Both of them perform the Git research the same way. They both learn from kernel history, although they learn different parts of that kernel history. And it's a really kind of unified approach that we came up with to commit analysis. Because if in the future we decide we need to classify commits separately for a different project, we already have that common infrastructure. And so this is kind of a summary of that, right? We have the ability now to easily classify commits, whether they are for backports or for CVs, or we may decide we want to do something completely new with them and build on top of that, right? It's all written in Rust, because now I know Rust so well, apparently. It's all fairly easy to work with. It's all open source, accessible. Oh, let me jump to this slide. There's references to everything from this slide, both to the commits I've shown that are landed upstream. This is the git resolve script, the commit that AI wrote to transform hash table. This is the Autosel tool. This is the shared infrastructure. This is really where the heavy lifting is. And this is the vulnerabilities Git repo. If you want to look at the Git history and look at the transformation from the bash code to the Rust code, but also if you want to look at the CV classifier within the vulns.git repo and see how that works, if you're curious. And that's all I had, if folks have questions. Yeah. There's no mic? Oh, there's a mic.
So you mentioned that your Rust refactor, or Rust code, you have tests that are written by the LLM. Okay. And I was curious with the kernel work. You're doing little refactors and so forth. I don't think I've ever seen kernel test code. It's been a while since I looked at the kernel. But is it generating tests for you, regression tests that are somehow shared so that the LLMs in the future can learn from that?
So the question is whether it's good at generating kernel test code in C, right? Honestly, I don't think I tried. It was really good for the Rust part. It definitely generated a whole bunch of Rust test scenarios based on examples we threw at it and examples it could find on its own from Git repo. I suspect it would be good for the C code. I had good experience with that. I never tried, though. It's a worthy attempt to see if it does a good job and it could just generate a whole bunch of examples.
Thank you for a great talk. Is it working? OK. So I think I would like to share something like 3 comments and 2 questions. So first comment, I think artificial intelligence is too brave definition of current state of the art. it's more machine learning, because we even didn't know what is natural intelligence. Second point, people is more cheaper from the point of power consumption. I see your point, but people is cheaper. And third point, very frequently, bug is something like new way to discover new feature. I discovered it multiple times. My question, okay, so it looks like that you invented the way to rewrite the whole kernel in Rust. What do you think about, can we rewrite the kernel in Rust by using artificial intelligence, machine learning?
I don't think we want to. I don't think that the goal of this is you can't replace humans, right? And sadly, or not sadly, the fact is that the humans who work on the kernel now, they know C better than Rust. I think that the kernel written in Rust completely would probably be a better thing for the kernel itself. It would be safer and like, memory safe and all of that. But you won't have humans that are able to work on it. At the end, it's the humans who matter. The LLM, as I said, is just a compiler for the humans to generate code. So if the humans are able eventually to interpret Rust code as well as they interpret C code, great. I just don't think we're there yet.
Okay, so let's consider such a way. Let's machine learning, artificial intelligence rewrite for us Linux and Rust, and then we will be trained by this stuff how to use this.
There was a recent project I saw recently on LWN, I guess, where it's a ABI compatible implementation of a kernel written in Rust, right? If anything, that's probably what you're suggesting, right? I think rewriting the whole kernel in Rust is going to be very challenging to LLMs at the technology level we're at today. They're really good at small, concrete tasks, as I said, right? The kernel is such a wide body of code that actually tackling all of it and doing that conversion perfectly is a questionable challenge to take on. The conversion we did for the bash scripts into Rust, we're talking about thousands or 2,000 lines of code, right? It's nowhere near the scale of where the kernel is. Maybe one day we'll be somewhere where AI can challenge that, but I don't think we're anywhere close to that right now.
Yeah, I think this is the current problem, that it's not so easy to rewrite something like driver in Linux kernel, because you need to have, for example, file system driver, you need to interact with VFS, you need to interact with memory subsystems, so it's pretty complicated. So in my next question, okay, it's about how we can use artificial intelligence, machine learning for something like analyzing commits, using Git and so on. But what do you think about using machine learning as something like new functionality in the kernel?
I don't object, but I also don't have ideas. I'm new. If folks find it, again, it's like compiler, right? If you find the tool useful to help you write something new, or to run AI within the kernel somehow, why not, you know? Just finding the use case. I think it's the use case that needs to drive.
Currently, it's not so easy to use machine learning in kernel.
It's not?
So one thing I worry about is, so you're generating some data like with Autosel that's giving a justification for a backport of a patch, right? And there's a tendency, I think, for humans to trust that justification. And eventually we're going to find a case where that trust was misplaced, right? But it seems like there's a possibility for errors to creep in there. I don't know if you have, I don't know if I have a real question here, but I have a concern.
I definitely agree with you that LLMs can be wrong. I also would say humans are wrong. Look at the amount of stuff we have in the stable trees. It's evidence of humans making a mistake, right?
Right.
We just try to make less mistakes. We can't eliminate all mistakes. Can LLM be wrong and give like a completely bogus description? Sure. I just hope it will do it less than the human counterparts that are working on that code.
Fair enough.
How can you know what license the code has that the LLM spits out? If it's compatible or not? Yeah, so if the LLM learns from an incompatible license,
Yeah.
and then provide that to you, and then you submit a patch set for review for the kernel.
That's a very lawyery question that I will avoid.
But has there been any discussions around that?
I have, I'm avoiding it mostly because I didn't think about that vector and I didn't try and tackle that. My impression was that it's on the companies that provide that service to me. When they give me code back, it becomes owned by me. And so me sharing it it's kind of my creative work.
I'll just make one comment there. If what the LLM is doing is finding other examples within the kernel source tree, then that's okay, right? Because it'd be GPL2.
Right, so when you're doing research work and it's looking at the Git tree and it does that, that's one thing. When it's coming up with code on its own,
Right.
I don't know where the odds of him finding the right code came from, right? In theory, it doesn't, so LLMs don't contain copies of code, right? It doesn't contain just like the kernel databases is. They only contain weights that help you guess the next word. So they don't contain snippets of code. They only say, well, if the block started with if, then maybe there's a then somewhere later, right? I don't think that the licensing matters too much, but I don't know. I didn't think about the licensing aspects.
Have you used any of the LLMs for generating I'm going to mispronounce it, the Kernel scripts? Because on Friday, I have a use case where I have 200 cases, 200 places in the kernel. It's a straightforward refactor, and I just don't remember the exact syntax and everything on there. So Friday, I spent a couple hours trying to get it to generate me the script to do like I wanted. And it was either two cases of one, either the script wouldn't even work, wouldn't even compile, or two, it would look straightforward, but then it would just, you'd run it and it would just make 0 changes on there.
I thought about it at some point. I think what I usually ended up doing though now is that I just ask the LLM to convert the 200 use cases and I give it a way to test its work as it goes forward. Maybe it's just simply building the kernel, right? Maybe just test every step with make. But I found that it's easier just to cut that middle step of it trying to generate something for something else and just tell it to go ahead and kind of go nuts.
So would you just if you had your subsystem, it doesn't matter, if you just pick a subsystem, will you just upload the 200 files and just say convert them for me?
If you look at kind of the state-of-the-art tools, if you look at Cursor or Cloud Code and all of that, they run locally, right? As a CLI. You don't even have to send the files. You just point them to your local Git repo and you say, hey, look at the subsystem and get to work. So it's very kind of transparent. It's just like calling another CLI tool, really, to go do your work.
Okay, thank you.
It kind of takes that annoying step you described in the middle of, okay, do I need to upload all the files somewhere and then download them, and then it just does it locally.
The two main challenges you brought up here, the backport and the CVE thing, where you kind of hinted at it already, that they're going after problems that already snuck in. Are you looking at how to get ahead of this and catching this, looking at the code before it actually gets merged or while it's on the mailing list type of thing, and reduce backports by not letting the bugs in the first place type of a thing?
Ideally, yeah. So we already have a whole bunch of bots, right, that can do things. Like 0 day is a great example of that, right? You send something to the mailing list, it will try and build it, and if it doesn't work, you'll get a mail, hey, it's broken, maybe you should fix it. LLMs can definitely fill a similar role in that. I think that the challenge that I saw in that is that this is a really large scale of work. And as the second question, as the second person who has the question pointed out, LLMs are still very expensive these days. And so ideally, we would be at the point where we can do that. I think we just need to grow the infrastructure and kind of wait for the price to drop a bit more. It's definitely something that would do well, I suspect.
I think so, yeah.
Okay, so follow up on my last question. So one of the main reasons I wanted to make the script was to make it easier for the maintainer to just say, here, like in the cover letter, I could put, here's a script I make, just run this, and then you could just diff what I made versus what you get with this and make it a little easier for them to review. Whereas if you just had something that LLM spits out, then it's just gonna be more review work. I was just wondering if you had a suggestion on trying to make it easier for someone to, it's easy to spit out 200, especially when you're talking about 200 patches or something. It's going to take time for people to review, and that's why I was trying to make it easier for that maintainer.
Yeah, I think in that case, you do want it to generate that. I think in that case, you also want to have it update check patch or something like that, right, to prevent it from sticking in. But yeah, if you have a specific need for the coccinelle script, then I haven't tried like generating something overly complex with it. I did kind of the basic stuff. I found that. So one of the reasons I quickly stopped doing it, because usually when you make those changes, there are also like variables and comments around it. I had the whole experience with Coccinelle like a decade ago where I eliminated one of the parameters to hlist, the one that iterates on the half list, right? But you also need to update a bunch of comments around it, the parameters being passed to functions, and then the uses are all different. And so when you run the Coccinelle script, you end up with like some noise around it that needs to be manually adjusted or just missed, right? And at that point, our documentation in the code base doesn't match the actual code, right? And that's why I kind of like the LLM thing where it knows to kind of look around it too, that the context window, the attention thing, where it can look, big block and know, okay, I need not only to update the variables, I also need to update this comment, I need to change this description. So I quickly stepped away from Coccinelle for this kind of work, and that's why I guess I rely more on LLMs. I would argue even that if you do that work and you share the script, then it's incomplete, because you will have cases like that where you have to change other stuff. I also trust each maintainer to just do its own, I guess, work. Like each subsystem is different, and they need to look at the code anyways. And if it is a trivial change, the Coccinelle usually does, then it should be also quick to just like glaze into like the hash table change, right? I think. Good? All right, thanks everybody.